So example 1 asks us to graph f of x equals 2 to the x power. So notice the structure of this problem. 2 to the x power. It's not 2 times x, it's 2 raised to the power of x. Right? X is representing a power, so as x gets larger, for example, if x is 6, 2 to the 6th power is 64. The numbers get rather large rather quickly. All right? So when I represent a power, I'm looking at the power itself. I want to pick x values that are not giant. I want the powers to be around 0 because small numbers are easier to work with powers. So if x is the power and that's all it is, it's not x plus 17 or 2x minus 5 or anything weird like that, it's just 2 to the x power, I typically pick -2, -1, 0, 1, and 2. That's my normal picks. Nothing magical about those numbers. They're small, they're integers. All right? 2 to any one of those powers is not going to be some ginormous number that's going to make me have to get a piece of graph paper that's like as tall as the ceiling to be able to plot the points. All right? Once I've established the numbers I'm going to pick, to get y, I'm just raising 2 to each of these powers. I can do a calculator to do that. So I'm going to, the power button is right here. So 2 to the power of -2. 0.25. 2 to the negative first power. -0.5. Or sorry, positive 0.5. 2 to the 0 power equals 1. 2 to the first power is 2. 2 to the second power is 4. If you know them, you don't have to type them in, but you sure could. So 2 to the 1, 2 to the 2. So again, just whatever you need to do. The base is whatever it is, and you raise the power. So you get points, just normal pick x, solve for y, plot the points idea. So -2 is 0.25. -1 is 0.5. 0 is 1. 1 is 2, and 2 is 4. That is what an exponential graph looks like. It's going to have a side that's coming down, flattening out, and a side that's going up. It doesn't necessarily go this way every time. Sometimes it goes that way. Sometimes it's underneath the x-axis, whatever. So it's wherever it is, but it's got that shape. It's got a flat side and then a going up side. If you take a look, we can see it's flattening out this way, it's going up this way. Now, when it comes time to connect the dots for an exponential graphs have asymptotes. Okay, an asymptote is an imaginary line that the graph is going to stay either above or below or to the left or the right of. That's what an asymptote is. Exponential graphs particularly have horizontal asymptotes. So there's going to be this imaginary line on this graph that the graph itself is not allowed to pass. All right? And if you see where the 0 power happened, and when it's 2 to the x, the 0 power happens when x is 0. If it's 2 to the x minus 5, the 0 power happens when x equals 5. So again, 0 power is not always just going to be x equals 0, but wherever the power itself is equal to 0, all right, which is this point, the side that's flattening out is going to bottom out at the next line down usually, unless something else is influencing it. So looking at this, 0.5, 0.25, if I keep on going left, if I just start randomly picking numbers bigger than negative, or less than -2, so -3, -4, and so on, 2 to the -3rd equals positive something. 2 to the -4 equals positive something. 2 to the -5 equals positive something. In reality, it's always going to be positive, right? No matter how big that number gets, because I'm not creating a negative number with negative powers. Negative powers make a fraction. 1 over 2 to the 5th power, 1 over 2 to the 4th power. So 2 to the -10th power, still positive. 0.0009. 2 to the -20th power, still positive. 0.000009. Right? They're getting closer and closer to 0. They're never going to reach 0. They're never going to be negative. So the asymptote is going to be a horizontal line at 0. And that's how we draw an asymptote. We draw a dashed line saying that this graph is never going to go past that line. Again, you simply, the side that's flat, just keep going that way with it, and eventually it's going to get close to a number. That's the number it's at. It's usually a whole number, an integer, 0. Sometimes it's positive, sometimes it's negative, whatever, but it's usually some integer value. And when I write the equation of an asymptote, a horizontal line equation is y equals number. So for the asymptote part of the stuff I'm supposed to identify, y equals wherever that line is. And that line happens at 0, so y equals 0 is the asymptote. I draw the asymptote before I connect the dots because that gives me kind of a fence. All right, imagine an electric fence. Imagine the graph's a teenage boy. Okay, teenage boys and electric fences. Electric fences, if you get close to them, they hum. They make this humming noise. I don't know if you've ever been close to an electric fence. Teenage boys hear that hum and they get drawn to the fence. That's just what happens. And ideally, they're scared to touch it, and hopefully it doesn't arc on them, but they want to get closer to it because it's like, wow, this is humming noise. That's kind of interesting. That's what, I think girls don't understand this stuff, but that's what teenage boys do. They hear humming things, they go closer to it. So that's what the graph wants to do. It wants to get close to the electric fence, which is the asymptote, but it doesn't want to touch it because it's scared to touch it. So that's what's happening there. So I'm going to connect the dots. I'm going to stay away from the fence here, and it's going to kind of approach the fence but never get to it. And then it starts going away from the fence, and then this side goes forever that direction. So as you connect the dots, be very aware there's an asymptote there. You don't want to cross it, you want to get near it. So as you get further left on this one, the graph's getting closer to the asymptote, but never ever reaches it. Once you get it graphed, the domain and range are very easy to establish based on this. The domain is where the graph lives horizontally. How far left and how far right does the graph go? Right? Well, it goes forever to the left and it goes forever to the right, which means that the domain is a set of all real numbers. Right, so again, domain, once you've got it graphed, you just look at it. What's the farthest it goes to the right? You can pick any number we want to, right? We can go as high as we want to go. The graph keeps getting higher and higher and higher as we go, but we can go that way as far as we want. We can go this way as far as we want. It gets closer and closer to 0, but there's no restrictions on what I'm doing. I can do 2 to any power. All right. The range is where the graph lives vertically, from the bottom to the top. Well, the highest it goes is forever, right? It goes to infinity. But it stops at 0. Does it ever reach 0? No. So when I do the range, and it's called f of x, so f of x, I'm going to say f of x is greater than 0. I'm not putting equals 0 because it can't equal 0. Two to any power that's negative is just going to be 1 over 2 to that power. Well, 1 over 2 to any power is going to be bigger than 0. So, intercepts are points at which the graph either crosses the x or the y-axis. When will this graph cross the x-axis? When will the graph cross the x-axis? Never, right? The asymptote's the x-axis. The graph can't touch the x-axis, so there is no x-intercept on this graph. If the asymptote were down 1 and all of a sudden it crosses the x-axis, that's possible. It could happen, but in this specific case, this is more often than not the case. This is a lot of times the asymptote y equals 0. If the x-axis is the asymptote, the graph can't touch the x-axis, but the y-intercept is 0, 1. This point right here is where the graph crosses the y-axis. So the intercept is 0, 1. And the final thing requested of us, I'll come up here, end behavior. What they're asking about with end behavior specifically is what happens as you go towards negative infinity, what happens as you go towards positive infinity. Negative infinity is over here, positive infinity is over here. They're asking what's happening to the graph. So it looks like this is how we write it. As x approaches negative infinity, it's the letter x, a little arrow, and then a negative infinity. To draw infinity, which I don't think you guys have done a whole lot of, two ways of doing it. One way, start here, come up a little bit, go through and down like that, around like that. Option two, you've done this many times in your life, you draw the number 8 with your paper on its side. Take your pick. If you have a smart paper, you can also like rotate it after you draw it. Turn your paper on its side, write an 8, then turn it back out. Now you get an infinity. So, as x is approaching negative infinity, what's happening to the graph? What's the y value getting close to? Y is getting close to 0, right? So as we go further and further in this way, the graph itself is approaching a value of y equals 0. So y gets closer to 0. As x is approaching positive infinity, going that way forever and ever and ever, what's happening to the graph? It's getting ginormous, right? So as I pick bigger and bigger and bigger values of x, y gets, we can say it several different ways, closer to infinity. We can say infinitely bigger. What do you want to say? Infinitely bigger. Let's go with that. Infinitely bigger. As we go that direction, there's no ceiling on this graph. It goes up forever and ever and ever towards positive infinity. So that's all end behavior is. What's happening to the ends of the graph? This is going up forever to infinity. This is flattening out to 0. As x goes to either negative or positive infinity, that's how you describe end behavior.